In terms of lower variance, which one?
2.
Sample 2, right, has a lower variance. By the way, no, so lower variance means lower standard deviation. We can talk about them interchangeably in that way. But now, do you buy that?
No.
Why not?
Sample size.
Sample size?
Well, yeah, I mean, you only have 2.
Well, so let's talk about what that is first, make sure everybody's on board.
Okay.
So sample 1 is 10 observations.
Yeah.
That's sample size. Sample 2 is 2 observations. And you're telling me this matters?
Well,
He said trying to look professorial.
no, I'm not.
No, me. No, me. I was trying to look for. You're saying this matters? No. So why does this matter?
Well, I think, like in any, like, well, for example, the real estate example, it wouldn't mean much.
Well, this is a real estate example.
Okay, well, it wouldn't mean much if my realtor gave me just 2 prices in my neighborhood and said, this is where I think your price of your house is gonna sell.
The bigger,
I literally
Why
did
not?
that. I literally
the
did
bigger the sample size, the more accurately it represents the population.
Oh, hold on. Somebody thinks somebody's sounding all fancy here.
What? I'm just
Christian.
eating Christian, like the religion with the K.
So let's. Oh, she's eating now.
It matters how significant or how comparable is the sample to what we're trying to predict. It doesn't matter if we have 10 samples,
Yes,
if
it
they're
does.
not close.
Hold on, whoa.
It
Okay.
always matters.
I'm not being harsh here, but he said something wrong. He said we have 10 samples. Here we actually have 2 samples.
No,
One of them has 10 observations. No, I'm just helping everybody learn the language of it. So like I said, not being harsh, I just want to point that out so everybody knows. Okay, so that's a very common thing people say wrong. So just another thing, don't say it wrong. This sounds smarter in a meeting, right? I don't care about in here, you're learning. Okay, so go ahead. So 10 observations.
The 10 observations seems that it's larger population, but we're trying to predict the house, a specific house that is more significant to the sample size that we only have 2. It might be better to use that one.
I'm not saying you're wrong.
But you're wrong.
No,
What are you looking?
I'm more saying I'm not sure I understand.
It depends on how big the sample is with respect to the population.
Why?
So the probability goes up, the bigger the sample size.
Because that will give us if it's good enough sample or not.
But why?
Because the
Hold on.
The perfect data set is your population, right?
You're.
The full population is the ideal data set, right?
Oh, well, okay, now. Okay, so first let me back off of your
Wait a
statement for 1
minute, I
second.
said the same thing.
So, huh? Oh, you said?
That is the same thing. No, that's a good thing. That's a good thing. No, that's a good thing.
She would have heard you except there's no grade for this part. So, this is the educator in me. Answering why something is very complicated. Okay? You might want to give a reason you think it's true, which is what I'd say you guys were doing. And you might, and you do, have very good intuition. But when you are answering the question why, you're not answering it for me. You should think you're answering for someone who's never talked about this. And just saying because isn't good enough. So we need to find something to relate it to the principles of what we're talking about. For instance, all of this is just trying to figure something out about the population, right? Well, population's a lot more. So at least there's some intuitive idea that having more observation is getting us closer to the population. That might be an intuitive thought, right? I think that's a pretty good one. Rocky.
With higher populations, don't you get a lot more outliers, which could also,
Good.
for example, if you do a population of housing sales in Atlanta, the average home value didn't up 300,000 or so until, what, 4 or 5 years ago? So
Okay.
you're counting historical data of $20,000 houses basing it on today's prices.
Well, so optimally though, as we add in X's, which we haven't done yet, but fair enough. As we add in X's, we would be able to account for how old, et cetera. So in the scheme of things, I think that issue would be taken care of. But you could be right that adding more in, even after we take care of all those issues, we have more outliers and things are more spread out. But to be honest, if that's true, we want our sample to tell us that. We don't want our sample to lie to us and tell us things aren't spread out. Does everybody see what I mean? So in some ways, having a bigger sample is gonna get us intuitively, and I'm just arguing intuitively, which is more or less what you guys were doing. I'm just trying to make it a little more precise. We're getting close, hopefully gonna get closer to what our population is really all about. Which is, and it's gonna have uncertainty, and right, there's gonna be some probability distribution over it. And that's okay, because that's the way the world is. But we wanna try to accurately portray the population, not just what our sample says. So, I don't wanna dig too deep into this, right, this second, but does everybody have a gut instinct that you, despite what we said about variance, you got a gut feeling that the one with more observations probably is better? Okay. So there better be some way of representing this in the way we calculate our confidence interval. Does everybody get that idea? So I'm gonna back up, I'll answer your question in 1 second. Everybody remember this? Actually, let me back up to the more complicated one. Don't worry about it, you don't need it. So, I already told you, all this comes from the data, right?
Yep.
And this comes from a distribution. This is like looking at the variance information. It's a square root of that, but whatever. So what better this Z do for us? If this just looks at the variance basically of our data, what do we need this other thing to do for us? It needs to somehow represent how big our sample size is, right? So there's a little bit of that here, but what we use right there better have something to do with that too. And in fact, it does, and that's what we're gonna talk about next. Who had the question?
Yeah, I just isn't it? And this could have been totally just from statistics courses, but I thought the minimum sample size needed to be like 30.
30. Had somebody, we were talking about that.
Okay.
Right.
We're just talking about that.
Oh, okay.
First
so
of
what
all,
was the answer?
that is absolutely untrue. But I'm
Okay.
not faulting you because I know it was said to you because it was said to me and it's probably said to anybody else.
Okay,
By the time we're done with this, I'll explain why they said that.
cool.
Okay? I'm serious. We're gonna fix all. I mean, wasn't it pretty interesting? I thought it was pretty interesting. I mean, for statistics. I have lots of cool interests too. I just happen to be good at this stuff. I like to sit down and watch TV.
Eat popcorn.
My life has changed a lot for decades. All right. Oh, that looks interesting.
All right.
You
Oh,
know
wait,
what?
mullet.
It does.
Let's actually calculate one of these confidence intervals. Actually, let's calculate two of them.
Let's do it.
Do it. Everybody remember 1.96?
Yes.
What level of confidence do we have if we picked 1.96?
95.
95, okay, we talked about that, good. So 37 is our estimate, right? It was the average. We're gonna subtract that off and add it back on to the table number, 1.96, times, then we have the standard deviation divided by the square root of observations. Everybody see that?
Yep.
That equals 32.6 up to 41.3. Does everybody get that? I mean, those, you don't have to, but if you plugged into a calculator, that's what you'd get. Question?
I don't know. Does this have anything to do with null?
We're working towards that.
Okay.
We're working towards
Because
that.
I'm like, this is getting very familiar.
Yeah, if you go back about 10 slides, it said we're doing how good the estimate is, and it said we're doing confidence intervals, hypothesis tests,
Yeah.
inferential.
Okay.
So that's all this stuff, yeah. Yeah, those of you that had this before, it'll be very scary how much you start to remember. For those of you that hadn't, good for you, because nobody's warped your mind yet. So we get this interval. Now for sample 2, we're going to do the exact same thing. 95% confidence interval. 37 minus plus 1.96 times its standard deviation divided by the square root of the number of observations, which was 2. That gives us 35 to about 39. Everybody, that's just what the calculation tells us to how it tells us to calculate. Looking at these intervals for 95%, for 95%, which one would you, before you even started this, in terms of the precision of your prediction, which one would you prefer to have?
Sample.
Number 1 or number 2?
Number 2.
Sample 2.
Yeah, everything else being equal, just blindly, you'd rather have the one that's not as spread out, right?
Right.
Wouldn't you prefer to go in and say 37 plus or minus 2? So 37,000 plus or minus 2,000? Or would you rather go in and say 37 plus or minus 4,500? See what I mean? So it looks like sample 2's giving you something you like more. Okay. Everybody with me?
Yep.
Okay. Now, ears wide open, please. There is a problem with this. The problem with this is that it uses a normal distribution. The normal distribution does not pay any attention to how big your sample is. Yet, every day one of you sat there and shook your head, yep, when I said, do you think intuitively the size of the sample, the number of observations should matter?
Right.
Right? Well, guess what? This really, really smart English person who worked for the Guinness Brewery, swear to you, thought the same thing. Genius. And said, normal's not right here. What is right? What is the proper trade-off between sample size and confidence? And he came up with the student's t-distribution. Okay. Remember, this is back before the internet and cable. So you know what he did in his spare time?
Math problems.
Math problems, statistics problems.
Charting.
Yeah.
He also did it at work, and he didn't want to get in trouble. So when he published it, he just submitted it as by student, so that Guinness wouldn't fire him for doing statistics on the job. True story. So it's called the student's T. The important thing is the student's T improves on the normal in this type of problem where, Kristen, you have small sample size. So it's not that you have to have 30, it's that they were telling you have to have 30 if you're using the normal distribution. And that's still not quite right. But we'll make it clear why they say that, or used to say that. Okay, so it's actually not the size of the sample that matters in the t-distribution. Something called degrees of freedom. But they're really simple. Degrees of freedom are the number of observations you have, in our case 10 and 2, minus the number of parameters that you're trying to estimate with those observations. Now that sounds all fancy, but all it means is, what are we doing with the 10 observations? We're using them to find the average. That's one thing we're estimating. With the sample size of 2, we're using them to find the average. That's one thing that's estimating. So the degrees of freedom, and get ready for the boom mind explosion. The degrees of freedom in this problem are
Anything other than
n minus 1. And that is not a coincidence. So it's the number of observations you have minus the one thing you're trying to estimate. By the way, what do you think it would be if you were trying to estimate 2 things?
N minus 2.
It works just like that. It's a beautiful thing. And the proofs, going back to what you pointed out with that proof, the proofs are very similar, but if you don't throw an n minus 2 in there, you do get biased estimates. Okay. So, everybody look up for just a second. A T distribution, actually, let me just get on the slide, okay. A T distribution is a pet peeve of mine. People say bell-shaped curve to mean normal distribution. Absolutely incorrect. There are lots of types of bell-shaped curves. Normal is one of them. So is the T distribution. The T distribution looks like this. If the blue one is a normal, the T will always be squunched down in the middle and fatter in the tails. That actually is a statistical term, believe it or not. Not just a Queen song, right? Some of you got it. But they're all bell-shaped curves. You want to guess what happens as N, the number of observations, gets bigger? What happens to the T? Well, this picture is trying to show it to you. This is for smaller N. With more N, it looks like that. For higher N, it looks like the red. And as you keep pumping up that N, eventually the T starts to look exactly like the normal. In fact, the normal is the limiting, there, we got limits in there. Look at us. The limiting distribution of the T. In the limit, the T starts to look just like the normal. But Christian, to your point, Thomas, to your point, once you get above 30 observations, they start to look so dang similar that lazy statisticians started saying, just use the normal. So here's the real point to you. Not everybody, I know not everybody. Have a lot of you heard that 30 number? So here's what used to happen before computers. Libraries literally had books, volumes of T-tables for different degrees of freedom. And if you want to be real precise, you had to go to the library, you had to look up the exact number to plug in, not 1.96, we'll see in a second what it might be, and plug it in. But for a professor given a test, what they said, well, as long as you got more than 30, the normal's close enough. The normal can basically be captured on one piece of paper, if you know how to make it dance and manipulate it and stuff. And so for the purposes of their class, normal was good enough. But they realized that even if you had 30, if you had 40, using the normal, you'd be off by a little bit in terms of your intervals. It just wouldn't be that much, so it wasn't that big a deal. So that you need 30 observations is, first of all, almost an anachronism. Nobody's going to be talking about it in 50 years. Because now, computers, Excel, SAS, anything else, uses the T-table for every one of their calculations. So you just don't even need the normal if you have a computer. And guess what? I got one right here. I never need to carry out volumes of books. Right?
So on the T-table, what is 95% of 30 degrees of freedom? Is it 1.96?
Huh?
On the T-table, 95% and 30 degrees of freedom, is that 1.96? Is that normal?
No, but let's take a look at what it says. So let me lead into this for everybody, but I was going to show, but I'll show it now. So T-table. First of all these tables are constructed from various points of view, so you got to know how to read this one. This one basically, you know at 1.96 how we plugged it in? The number we're going to plug in for 95% is just this column. It's this 0.05 two tails that gives that away. We're not really into that yet. But we're going to plop it out of this table. You'll notice as we go down, this goes from 12.706, drops to 4.3, a real big drop, and it keeps dropping. And down here at 29, it's 2.045. And at 30, it's still not 1.96, it's like 2.043 or something like that. And then all of a sudden it says large, whatever that
So as
means.
it approaches infinite.
And what that all it's really trying to represent is in the limit, it would be 1.96. So even at 30, 2.043 would still be off of 1.96. So our interval, if we use 1.96, would be a little thinner than it really should be, but it's fairly negligible, is what all of your stats professors were telling you back when they did that. So there is not this fictitious number 30 that you have to have. It's that you need 30 if you're going to rely on the normal distribution. That said, no computers rely on it anymore. There's really no need to. So, there are lots of important things a normal distribution does in statistics. So I'm not saying don't use it, but just in this application, you don't need it. So let's talk about, instead of that 1.96, what we should have plugged in there. And so, how many degrees of freedom do we have from sample one? Sample one, that was 9, right? 10 minus 1. So we come down here to 9 and we find 2.262. So we started off by saying we want 95% confidence, right? And then, so just the way this table is constructed is, this 0.05 is kind of like your lack of confidence. Okay. So we had what, 2.262. How many degrees of freedom do we have for the second sample?
1.
Yeah, 2 observations minus 1. That's 12.706. So before you even put the numbers in there, can you tell what's happening?
Yeah.
We think, intuitively even, that if we use fewer observations, that's a bad thing. But in terms of the interval, how do we represent a bad thing? We make the interval be bigger. And how do we make the interval be bigger? We multiply the standard error by a bigger number because that pushes it away from the estimate more. Make sense?
Mm-hmm.
So let's actually take a look at what happens when we do that. So now I've plugged in 2.262, and I plugged in 12.706. And when I make these calculations, look at the confidence intervals I get. Which one do you like more now? The first one, right? It's actually pretty close. It's pretty close because I chose, remember, I got to pick the second sample. So I picked it to be really dead on around my estimate for this purpose. But once you account for, once you have the t-table help you account for the sizes of samples, it starts to dominate just like your intuition told you it should. Make sense? Okay. So, all this said, this will not be part of any assignments. Well, part of the assignment you are going to have for this will have you calculating confidence intervals. Hopefully now when you calculate them, actually, not by hand, Excel will calculate them for you. So we're not doing anything tough here. Now, you need to be able to look at it and tell you what's going on. And hopefully with that background, you'll know where it came from, okay? By the way, and when we get them in Excel, when we run regressions, we'll talk about that. Okay. Okay. I'm back. Okay, so we're gonna switch gears here now. So we're gonna talk about hypothesis testing after we actually try to run a regression. Let's get our computers open and try to get this running so that during the break I can help people fix it without wasting class time. So if you have your computer, get Excel out. Who are the weird Mac people? Good luck. Actually, in the last version of Mac, Apple actually made it much easier. I believe they embedded regression analysis. Finally. You used to have to go get an app on your computer. But I think they fixed it. By the way, I have a Mac in my office. I just get it.
I mean, it's an app on Windows. It's an app on Windows 10. Oh, wait.
Okay, so what else do we have? Size. Would somebody mind reading the size numbers off to me? The X values?
Oh, is it one in your, okay, I didn't know.
Maybe I have 15.
19, 49, 42, 41, 40, 18, 27,
25. That look good to everybody? Just double checking it. All right, so y'all go ahead and get those in columns A and B,
Yeah, what's that first?
and make sure in row 1 you give it a name, price, size, something like that.
Is this in Moodle? Or did you just?
Yeah. The Excel's not
Not
Moodle,
Excel.
the PowerPoint.
No.
Oh, okay.
Yeah, I kind of wanted you to create this Excel from start, just so kind of get our hands dirty, so to speak. If this were like thousands of data points, I wouldn't have done that to you. But I figured 10 wasn't too much.
You don't know us very well.
Do you have that plugin?
You guys getting it going?
Yep.
I'm watching my son's first at bat. so I'll be looking Ah. Oh, I was wondering why they texted to me. So, yes, I'm missing a baseball game for this. So I also, yeah, but
You know what?
Ser-
My son has a
seriously, who are the funnier people in here? we're gonna set
Rocky.
Allison up. You, and if you don't believe
This
it,
whole row.
just ask her. She's modest too. I'm just- So,